So guys, this is the power supply that I made in one of my previous videos for charging my inverter battery. So here I'm going to use this power supply to run the water pump. So guys, the water pump is ready, and that's the power supply that I have to connect, and that's the 220 volts mains. And this is the tube well that contains water. The first step is to connect this pipe. Okay. And then take the other end of the pipe and throw it in the well. So guys, here you can see that I've connected a 12 volts power supply, and I have removed the strip connection system. There is a lot of vibration although, and it is going to smoothen with time. The initial rectifier died, because of which I had to connect two rectifiers in parallel with a heat sink. Okay, so turning it on. Go. Let's see. Whoa. Whoa. Actually, you see the pressure is really good. Wow. So guys, this time I provided this support so that the pipe does not bend with the suction pressure, and then the pressure output is going to be good enough. Okay, turning on the pump. You see, very high pressure. Cool, right? Very nice. That's the power supply. Oh, the bucket is getting empty. And we are done. So guys, this is my 400 watts solar panel setup, and now I'm going to use this setup to power up my water pump. I've already connected the positive wire. The negative is over here. And yes, I forgot to mention one more thing. You see this pipe? The pipe is like this and going here inside the tank, the water tank. You see? So let's connect the left out terminal. Nice. So guys, now I'm going to use this a buck converter, like 48 volts to 12 volts and a max up to 25 amperes output, and let's see if the pump performs better this time. So one terminal is left finally, the black one. Whoa. Whoa. Super far. Oh, very good pressure. Around 18 amperes is what I am getting from the buck converter. And the sun is a little low right now. It keeps on getting cloudy. Hi guys, look what I found. A 40 years old General Electric oilless pump. Let's have a look at its label. Here as you can see it states 12 volts and 11.3 amperes, which are quite high, and the RPM of the motor is 3450. The date of manufacture which is 3rd of March 1982, and they have also provided the toll-free number. So before opening it up, let's give it a spin. Here I'm gonna use this 220 volts to 12 volts power supply that I constructed using a UPS transformer for charging my inverter battery. The output voltage is 15.6 volts. So the voltage has dropped to only 10 volts, which means that this machine is drawing huge amount of current from the power supply. Let's check the amperes. Stabilizing at around 6.5 amperes, so it was quite high for no load current. You see, I'm putting my hand on the outlet and it is getting loaded. Okay. 12 amps constant. But there is still one big problem, that the voltage is dropping from 12 volts to as low as 7.5 volts under full load. So for that, I'm going to change the transformer output winding tapping from minimum output to reach maximum power output. The new output voltage is as high as 32 volts DC. Yeah, there's going to be a huge spark. So here I'm going to use this high temperature plastic sheet. Let's put some pressure on it. So the maximum we did was around 18 volts, I guess. 16 volts. This motor is performing very good. I'm pushing it at the maximum performance or power output. So the amperes are rated around 11.5. Once again, you see 11.3. Now let's increase the load by putting a finger here. Max 21 amperes, very high. Wow, seriously, the output pressure of this pump is very high. This is the rotor, and here they have used some really cool technology. When this pump rotates, these sliders come out and the air in between the two sliders gets trapped, and then this air is taken to the exhaust chamber. This is the exhaust chamber and this is the exhaust nozzle and this is the inlet. So air is going to get inside from here and then come out from this slot, you see. Let's open up the rest of the motor. Now comes the close-up for the armature or rotor winding. As can be seen, the bearings are very high quality and it's printed on it NTN Japan, which says that it is made in Japan. As for the copper winding used in the armature, very thick copper wires have been used to carry huge amount of current. No wonder when I forced it at high power input, the current peaked at 21 amperes. The construction of the armature is similar to today's DC motors. There is no difference except for the quality, and the armature winding, it is so thick that it is somewhat like that of a bike starter motor. I won't say car starter motor because in that case the armature winding is even thicker, but compared to the bike starter motor it is identical. Seems like this pump wasn't used much. There is some rust present on the poles of the armature, but that is acceptable since it's been almost 40 years since this piece has been manufactured. Now let's get an inside view of the field winding of this motor. So as can be seen here, this pole is obviously an electromagnet type. It's not permanent magnet. These are the windings. I gave another look to its label and it was written DC compound motor. Let's place it back as it was before. Now there is one pointer. Always make a mark with a permanent marker on the disconnecting parts of a machine, and this way you will know for sure which side was connected to the rest of the body. Let's close it. So now that we have assembled it back, let's test it. Hi, today I'm going to make a universal motor speed controller. And this what you see is the machine that runs on universal motor. It's a vacuum cleaner, a dead one. So that's the inside view. You see the universal motor? I have to take it out. So here is our high-speed universal motor. And as you can see here, it is 1000 watts. And that's the impeller. Also, if you have an idea where I can use this impeller, let me know in the comment section. This is a 9 volts to 24 volts variable DC supply, and I'm going to test this motor with this supply. So the motor is working. Let's do some oiling. Now it is running pretty good. So let's make our own speed controller. Components needed for this project are MJE13009 power transistor, variable resistor, 100 kilo ohms, and a 35 amperes bridge rectifier. I also plan on using this capacitor for better starting torque for the motor, and we are also going to need a heat sink. I'm going to use this one. It has 6 MOSFET slots, so I can easily mount 4 transistors on it. So that's the max I could do. It's much better than before at least. And all the transistors that you see in the front will be connected in parallel. So guys, here I'm going to use this universal board. Here the green wire represents common positive for collector and black one represents common emitter for negative. So here, as you can see in this video, I'm doing the step-by-step transistor connection. 3 transistors are being used, each 13009, and all the 3 are going to be connected in parallel, meaning base to base, collector to collector, and emitter to emitter. After that, another transistor is used to drive the base of the original 3 transistors, and then to the base and collector of the driving transistor I have connected the variable resistor, and the circuit looks somewhat like this. The output is variable output from 0 volts to 120 volts DC, and input is 120 volts DC. So guys, it's time to connect the rectifier, and here I have already connected the wires to the AC terminals of the rectifier. Now to the remaining 2 terminals, which are DC, these 2 wires will be connected. Done. This is the supply. At present it is turned off. Now it's time to connect the universal motor at the output. So guys, here I'm going to start with the 500 watts sewing machine motor. So let's turn it on. You see, it has started running. That's your home supply and the rectifier that is converting home supply to DC, and after that comes your circuit. And at the output I've also placed this rectifier, as I said before, and that's your motor, although it's 220 volts, but I'm running it at lower voltage, so the RPM is a little low, but still it is running quite good. Let's increase it. Now guys, let's try this vacuum cleaner motor, 1000 watts. Okay. Let's increase the speed. Whoa! Close up for vacuum cleaner motor. Super close up for the vacuum cleaner motor. Turning on the switch, slowly increasing the speed. It has started running. More. Now guys, let's test this circuit on this super big washing machine motor. Okay. Increasing the speed. More. And guys, you can also use the same device on DC motors. Obviously the voltage rating is different for this motor. I'm going to run it at 50 volts, although it is written 40 volts here. Yeah, no heating at all. Increasing the speed. Fine. More. 50 volts input from an e-bike charger. Now guys, what will happen if I connect this 1 kilo ohm half watt resistor to the output terminals of this speed controller circuit? For input, I'm using the same 50 volts supply from the e-bike charger. Let's connect the multimeter to check the output. Here it's 3.127 volts, and remember that the input is around 59 volts max. Let's reduce it and see how low we can go. You see, as low as 0.5 volts DC. Yeah, 4.1 volts almost. That is best for charging your lithium ion batteries. Let's go for 5.1. This is the voltage at which your mobile phone charges. 6 volts for your 6 volts lead acid battery, usually used in emergency lights. Your rechargeable 9 volt batteries. And again, we can go or increase to as high as we want. So as you can see that this device is just perfect for charging your batteries. Okay, and here as you can see that we are doing full. Pretty good, huh? But what if we don't have an e-bike charger? We can always use our old laptop chargers and charge our 12 volts batteries. Setting it to 14.4 volts. Very smooth increase in voltage. Yeah, we have the exact 14.4 volts. So let's connect it, and the voltage drop is around 12.16, and the battery is charging. With time it will increase and finally reach 14 volts when I will claim it fully charged. Oops, it has auto turned off. So guys, as you can see that it has gained 13.27 volts from 715 to like 740.